वेरी वार्म ग्रीटिंग डियर व्यूवर्स। आज के फिज़िक्स लेक्चर में मैं आप सबको खुशामदीद कहता हूँ। आज का जो हमारा टॉपिक है फोर्स एंड मोमेंटम, इसमें हम कुछ ऑब्जेक्टिव्स के बारे में डिस्कस करेंगे। स्टेट द रिलेशनशिप बिटवीन फोर्स एंड मोमेंटम, डिराइव द फिजिकल रिलेशन बिटवीन फोर्स एंड मोमेंटम, डिफाइन इम्पल्स, tells its mathematical form, tell 5 examples of impulse and collision time. First, we will see what is the relation between momentum and force. Suppose we have a force, a steady force, constant force acting on a body of mass m. Then its velocity increases from u to v in time t. Here, u, small letter u, which represents initial velocity of the body, and the small letter v, which represents final velocity of the body. In some textbooks, the initial velocity is represented by v, I. In a subscription there we write small I, and the final velocity that is represented by vf. In subscription we will write small f, and the variable that is used to represent time, that is t. And when a net force, unbalanced force, acts on a body, then it produces acceleration a. And then we know that acceleration is denoted by mathematically a equals difference of final and initial velocity over time. Now we are going to multiply both sides with the mass factor m. So we will get this equation am equals m into v minus u out of t. So according to Newton's second law of motion, that we know that when a net force acts on a body, it produces an acceleration, and the magnitude of acceleration is directly proportional to the force and inverse proportional to the mass of the body, and that is mathematically represented by as F is equal to ma. So on the left side of the above equation, am can be replaced by f. So f equals mv minus mu over t. So from here we can say that on the left side it shows the applied force, the net force, the unbalanced force that acts on the body, and on the right side of this equation we can see the numerator that represents the change in velocity, and the denominator that shows the time taken for that change which occurs in the momentum. So force, applied force, is equal to the rate of change of momentum. So this is the relation between force and momentum. The rate of change of momentum is equal to the applied force, or the applied force is equal to the rate of change of momentum. And as you know that force momentum is measured in Newton's second or kilogram meter per second. Now let's move towards the next topic, that is impulse. The force that acts for a short interval of time, that is called impulse, which is represented by capital letter J. J is the symbol of impulse, which is equal to F times T. F times T, which is the product of applied force and the time of impact or collision of two bodies. So on the other side, we can also represent impulse as J equal to change in momentum, right? So impulse is also equal to change in momentum. Remember, force is equal to rate of change of momentum, but impulse is equal to simply change in momentum. And the unit that is used to measure impulse, that is Newton's second or kilogram meter per second, similar to the unit of momentum. And this impulse is also a vector quantity. Here I have given an example, right? Note this point, very important. The force felt during an interaction depends on how quickly or slowly the momentum changes. A longer time separates over the impact, making the force smaller and safer, even though the total impulse remains unchanged. So if the time of collision, time of impact is large, then the impulse force become very small, and that cannot hurt the body. And here I have given an example, right? And the other on the uh, top of this picture, here I have taken a picture, right, which has no hairs, a bald headed person. And the other, it's my own picture with hairs, right? So which one do you think how this relate to impulse force? So which one has more um, vulnerable to hurt by a constant force? So yes, you know that the hair that increases the time of impact. So the person with hair has less chance of hurt by the force as compared to the person who doesn't have hair, who is a belt-headed person. So here the time of collision will be very small, so the impact of force will be very large. But in the second case, in the latter case, the time of collision will be large and the force will be small, and its impact will also be small. So here's another example: batsman following through after hitting the ball. So the good cricketer or tennis player follows through with the bat or racket when striking the ball. The force applied then acts for a longer time. The impulse is greater, and so also is the gain of momentum and velocity of the ball. So there is a greater chance of making 6 or 4 runs in this case if we follow our bat in the direction of the cricket ball. So it increases the force that is acting on the ball. As a result, there is a greater chance of making 6 and 4. Another example is here: cricketer drawing back the hands to catch the ball. When a cricketer wants to catch a moving ball, however, its momentum has to be reduced to zero. An impulse is then required in the form of an opposing force, acting for a certain time. The cricketer draws his hand in the direction of moving ball, then an average force is then applied for a longer time. In the first example which I have given here, the force acts in the direction of the ball. So when the time of impact is large, in this case, then the force becomes very large. Here, the force acts against the direction of the motion of the ball. So here, if we increase the time of impact, then the force becomes less small. So the injury will be small in this case, and the chance to lose the cage also becomes very less if we draw our hand in the direction of motion of ball. And third example, crumple zones in vehicles. The front ends of modern cars are designed to crumple during collisions. Crumple means it bulges inside, folds inside. This safety feature is called crumple zone. In a car crash, the car's momentum is reduced to zero in a very short time. If the time of impact can be extended by using crumple zones and extensible seat belts, the average force needed to stop the car is reduced. So the injury to the passenger should also be reduced or less. And the last and fourth example, sand reduces the athlete's momentum more gently. The use of sand gives a softer landing for long jumpers. As a small stopping force is applied over a longer time, the injury to longer jumpers will be less. On the other case, if the longer jumper jumps on a hard and solid concrete land, then the chance of injury will be very large, will be greater. And the last example, fifth example, use of soft material for packing fragile objects. So fragile objects such as glass, walls, etc. are packed with suitable materials such as styrofoam, rings, balls, polythene sheets with air sacs, etc. Air enclosed in the cavities of these materials make them flexible and soft. During any mishap, they increase the impact time on the fragile objects. An increase in impact time lowers sorry lowers the rate of change of momentum, hence lessen the impact of force. This lowers the possible damage due to an accident. So if these soft objects, right, they increase the time of impact or time of collision, right, and decrease the force that acts on the fragile objects. And then there will be less chance of damage due to an accident. So thank you very much for watching.